Hello guys, we are going to talk about Newton's third law. Specifically within this video, we're going to talk about how to identify paired or action and reaction forces. Newton's third law is the idea that for every action, there's an equal and opposite reaction. Now, you might have talked about this in previous classes, and maybe you've heard this term before. Throughout this unit, we've been talking about Newton's three laws. The first law is an object in motion will stay in motion, and an object at rest will stay at rest unless acted upon by a net force. The second law is the idea that that net force is equal to mass times acceleration. And the third law is really looking at how do objects interact with each other. So Newton's third law, let's revise it a little bit. We're going to say whenever one object exerts a force on a second object, that second object also exerts an equal force on the first object. So I'm going to look at this specifically and think about a bus. If a bus is driving and it hits a bug, the bus is going to feel a force from the bug. But the bug also feels a force from the bus. So we're going to use that idea to go into the rules for Newton's third law pairs. The first rule, it must be two separate objects. So in this, we've got the bus and we've got the bug. So that works out. We also have to be acting in different directions. You can see here that we've got a rightward force. That's the force acting on the bug. And then we've got a leftward force, which is the force acting on the bus. And they must be equal in size. Now, we can't see this in our drawing because we can't measure, like I just drew arbitrary lengths. However, I want you to take my word for this, that those are going to be equal. If you're really struggling with the idea if they're equal, I've got force sensors. I can prove it to you. So let's look at some actual examples. We've got Ben and Rhonda, and I want to figure out what the paired force between them is. So I'm going to start by drawing a force diagram for each of them. So I'm going to start with Ben. Now Ben, he's got force gravity, and I'm going to say force gravity on Ben, I'm going to say big B, by the Earth. I'm going to label this out because it's going to help us identify what that paired force is between the two of them. Now we also have a force normal on Ben by the ground. I'm not going to say by Earth because I save Earth for when it's like gravity. And he's got a force tension acting on him. Force tension on Ben by the rope because that's what causes the force tension. And then he also has a friction force acting on him. Friction force on Ben by the ground again. So those are all of Ben's forces. Now we're going to do the same thing for Rhonda. Rhonda has a force gravity acting downward. Hers might be less because she might weigh less. On Rhonda by the Earth. We've got a normal force on her. Force normal on Rhonda by the ground. She has a tension force acting on her. On Rhonda by rope. And then she has a friction force acting on her. Force friction on Rhonda by the ground. This on blank by blank, this is just a on by statement, which is just really helping me identify what is feeling the force and what is dealing the force. Now looking at this, when I'm identifying the paired force, I want to identify the force that is causing these two objects to interact, which would be what's the force that causes Ben and Rhonda to interact with one another. Now, right away, my brain is going to jump to this tension force is going to be the force that's causing them to interact because that's the thing that they're both touching that allows them to pull on one another. We can also check this by saying, okay, is it on two separate objects? Ben, Rhonda, yes. Are they pointing in opposite directions? One's pointing to the right, one's pointing to the left, yes. And are they the same size? The answer to this one is yes, because if we were to put a force sensor between the two of them and connect two force sensors and pull, you would actually get the exact same force. I would actually encourage you to do that. If you want to go grab some force sensors from the back of the room or some spring scales and pull on both sides, you would see that those read the exact same if you were to do this yourself. So our paired force here is the force tension. So look at this with a cake. We can break apart our cake in any way we want. I'm going to first say, let's look at, just do the simplest one. We're going to look at the cherry as one of our things. And then we're going to look at the whole cake as the rest of it. So thinking about the forces acting on the cherry, we've got force gravity on cherry by Earth, and there would be a normal force on cherry by the cake or the surface it's on. Now, if we're going to do this, I'm going to move my face up here. If we're going to do this with the whole cake, I'm going to draw, and we've got force gravity on cake by Earth. We've got a normal force on cake by the platter or plate or whatever you call this thing below here. And then we also have an applied force on cake by the cherry. Now looking at this one's a little bit more complicated to decide what that paired force is. Now with the cherry, it's probably easier to start with the cherry here because it only has two forces and then figure out what the matching force is on the cake. So looking at this, I don't look at the Earth. The Earth is not one of the things I drew the force diagram for. So I'm not worried about what that paired force between the cherry and the Earth is. I'm curious about what the cherry and the cake is because that's where my interaction is. So I know this has to be one of my two paired forces. So I can see it says on cherry by cake. So if I go to the other object, I'm going to look for what that force is on the cake by the cherry. So on cake by Earth, no. On cake by platter, no. So this one, the paired force has to be this on cake by cherry. And again, we go through that checklist. Is it two separate objects? Yes. Are they pointing in opposite directions? Yes. Are they the same size? They're not drawn the same size, but I know because it's the interacting force that they are the same size. That's a big thing when we get into that calculation piece we're going to do. All right, I've got one more example in this video. Thinking about when you walk. This one, the forces are kind of already drawn, but I want you to think about as you walk and you're walking along the ground, you are pushing on the ground backwards. So this is if I were to do a force diagram for the ground would feel an applied force because you are pushing back on the ground. If you push on your foot, you can feel it. The force that makes you go forward, because the ground pushes back on you, is a force friction in the same direction you walk. That's why most of the time when we're doing physics problems, I say you're sliding along the ground. Because if we were to say walk, our friction would throw things off. You're not going to see this very often, but I do want you to keep this in mind that friction can go the same direction you're moving because it's the friction that's propelling you forward from the ground. All right, that's it for this video. In the next video, I'm going to go into how can we take these multiple paired forces and put it into the idea of using it for calculations.